In 3.3, we're going to talk about simple random samples. We talked about previously that those are the best types of samples, and how we're going to talk in this lesson, how do we get them? So in 3.2, you learned that choosing a sample at random is a good way to avoid bias. In this lesson, we start with the details of how. How do you get a random sample? So, definition. Simple random sample, which we'll abbreviate SRS, of size n, is a sample chosen in such a way that every group of n individuals in the population has an equal chance of being selected as the sample. So in a simple random sample, each sample of size n has the same chance to be chosen. This implies that each member of the population has the same chance of being chosen as the next. That's an important concept to capture here, okay? That there's not leaving anybody out when you choose. Now, you can use technology to choose a simple random sample. This is easily helpful when the population is large, and this is the steps you'll need to use, and I'll show you more on the calculator. Label, use it with technology, first thing you have to do is label. Give each individual in the population a distinct numerical variable from 1 to n, where n is the number of the population. Okay. Randomize. Then we use a random number generator to obtain n, different integers from 1 to n. And then select. Choose the individuals that correspond to the randomly selected integers. Okay? So let me show you what this looks like. So in your calculator, I'll show you more of this in class. If you click on the math button and you go over to the probability, the fourth thing over, the fifth thing down says randint. That's a random integer. Okay? And what you would do is you put 1 and a comma, and let's say we have 100 people in a population we're trying to survey. Close the parenthesis, and then if you hit enter, it's going to randomly choose a number between 1 and 100. Pick 91. Great. Then I go to the one that I numbered, 91, and get the information from them. Then I could go again, and then look, it shows 15. And again, it shows 52, and so on and so forth. This is a random number generator that you can use in your calculator. It's pretty easy to use. It's not perfect, but it works pretty good for our class. And I'll show you more of this again. When Mr. McCourtney's class did the activity about the Federalist Papers, his students got results as shown below. When we did the random sample, like we did in class, the averages were lower, right? But we know the true average word length is 4.9. So where does that line up? Which one was better? Well, the random sample was better. It was more the center of this one. On the student sample, without any randomization, it was not even close to the center of the distribution. So what you need to capture is that the fact that different random samples of the same size from the same population produce different estimates. This is called sampling variability. All that means is my sample is different than your sample. If it's completely random, we're not going to have the same answers for our sample. Okay? That's just the bottom line. It's the way it works. And we will see this a lot in class. Sample means vary. Even though the samples are selected from the same population, we can reduce the sampling variability by using a larger size. So here's the Federalist Papers. Let's say we chose only 5 words. We did a random sample, but we only chose 5 words in our sample and found the mean of them. This is what the distribution might look like. But notice what happens to the distribution if we chose 20 words and averaged those word lengths. Notice that the variability got much smaller. This distance is much smaller, the range of the data, if you will. Okay? But that's because the sample size got much bigger. And that's a really big concept for us. We're going to use it a lot this year, so make sure you see that. So let's try an example. The purpose of a sample is to give us information about a larger population. The process of drawing conclusion about a population on the basis of sample data is called inference, because we infer information about a population from what we know about the sample. All right? So it's called inference. We take the sample, we collect data, we make conclusions, and then we draw conclusions, and we assume it's true about the population because we took a good sample. All right, so let's put some of this to practice here. It says the school newspaper is planning an article on family-friendly places to stay over spring break at a nearby beach town. The editor intends to call 4 randomly chosen hotels. to ask about their amenities for families with children. They have an alphabetized list of all 28 hotels in town. Now, describe how to select a simple random sample of 4 hotels using slips of paper. Okay, we're not using a calculator, we're just using slips of paper. So here's what you would do. You're going to have to list out the steps. First thing you would do is give each hotel a distinct number, distinct label, 1 to 28. Okay? And then you would number 28 identical slips of paper, be identical, and then you would put them into a hat. You could say put them in a bowl to draw from, whatever. Equally. Okay? Then the next thing you would have to do is select 4 strips of paper from the hat, and you would call the 4 hotels that you selected. Okay? That's how you do it with paper and pen. Real easy. Right? Give each hotel a distinct label, 1 to 28. Number 28 identical slips of paper and put them into a hat. Select 4 strips of paper from the hat and call those 4 hotels that you selected. Now, B says, describe how to select a simple random sample of 4 hotels using a random number generator. So this is using the calculator, but you still have to do a few steps. The first thing you got to do is, again, give each hotel a distinct number or distinct label, 1 to 28. All right. Now we don't use slips of paper. We're going to use a random number generator to generate 4 integers, okay, or you could say numbers. But you need to make a comment here that if sometimes those generators will give you the same number twice. So you want to say you're going to ignore any repeat. Okay. Then 3, you're going to then call the 4 hotels you selected. Okay. So there's 2 ways to do a simple random sample. One with pieces of paper, one with a random number generator. Moving on. In a simple random sample where n is 6 students from a Washington high school, the correlation between arm span in centimeters and height in centimeters is r equals 0.928. Do you think that the correlation between arm span and height for all the students at the school is equal to 0.928? Okay, let's think about this. They picked one sample of size 6. Do you think that sample is perfectly representing the whole population? No. Okay, this is going back to sampling variability. One sample may be different than another, so they're going to have different R values. Okay, so the way you would put your answer is this. You'd say no. Different random samples will produce different correlations. Okay, so, and then you add on, it is unlikely that this sample correlation is exactly correct. Okay, it's just not going to happen. It's really unlikely. Okay, so anytime it says, is it equal to that? Probably not, because it's just a sample. Now, B says, if the sample size is increased to 100 students, what effect would this have on the estimated correlation? Well, the correlation may not be exactly right, but it's probably closer to the right answer, okay, because our sampling variability is reduced quite a bit, okay? So we would say because the sample size has increased, we expect our estimate to be closer to the true correlation. All right, because it's bigger sample size, less variability, more accurate result. So number 3, the big example. Make sure you really listen here. When a coin is flipped, we all know that the probability of a coin lands on its head is 0.5. However, what if the coin is spun? 2 Polish math professors and their students spun a Belgian euro coin 250 times. It landed on heads 140 times. One of the professors concluded that the coin was minted asymmetrically and was more likely to land on heads. A representative from the Belgian Mint indicated that this result was just chance. Well, to determine if these data provide convincing evidence that the Belgian euro coin is more likely to land on heads, 100 trials of a simulation were conducted. Each dot in the graph shows the number of heads in a random sample of 250 spins, assuming the coin has a 50% chance of landing on the heads. So what does that mean? They did this, they flipped the coin 250 times, 100 times. They did that same thing 100 times. And they plotted on this dot plot how many times they got heads for each experiment. Okay, so there's a 140 in there. Okay, and we're trying to see how likely is it that you would get a heads 140 times. So we do the same simulation over and over and over. We did it 100 times here. All right. Now from this we have some questions to answer. Explain how the graphs illustrate the concept of sampling variability. Okay. Well, if you look at this, you have one sample had heads only 105 times. One sample had a head that's, 142 times. That's a big range of values right there. And that's because of sampling variability. Not every sample is going to come out the same. So we put this in words. We say if we repeatedly take random samples, size, in this case, 250, we did it 250 times, from a fair coin, the number of heads in the samples vary from 105 to 142. Okay, that's a big variation, right? Now, B, this is part B. Based on the results of the simulation, is there convincing evidence that the Belgian euro coin is more likely to land on heads? Explain. We did this 100 times, right? So there's only 3. So a 3 out of 100 is 0.03, right? Or 3%, okay? So, because only 3 trials out of 100 had more than 140 heads, there is convincing evidence that the Belgian euro is more likely to land on heads. Okay? So we call that convincing evidence. Now, how do I know it's convincing? If it's 3%, right? 3%. The bottom line of convincing evidence, if it's less than or equal to 5%, then it's convincing evidence. So 3% is less than that. So because it only happened 3% of the time, that's pretty convincing that it didn't just happen by chance alone. Okay? And we're going to explore this concept a lot through this course, so don't get frazzled if you don't get it right now. But you're looking at, okay, how many times did that happen in my simulation? Well, only 3 out of 100. That's only 3% of the time. That's convincing evidence of whatever it is they're looking for. In this case, that the Belgian euro coin is more likely to land on heads. All right, we'll talk more about this in class. See you there.